Good morning. Uh, how are folks doing? Can you hear me? So we're going to continue our discussion of rotational motion today. Let's see. Who do we have? Caleb, who else is here? So we're in our last lap for class. Let's see. I got your quiz last night. I'm going to try and get everything that's outstanding graded as quickly as possible so you know kind of exactly where you stand. Although I have a kind of a pile of labs and stuff to look at, so I'll be working on that today. And well, in the rest of the week. But I will reach out to students if I see anything in the grade book that's like if something's missing or something. But also, if you scrutinize that and see something that looks like an error, like it's in error, let me know. We'll get it straightened out. It's a little bit awkward online because we don't have any face-to-face like opportunities. So I'm apologize in advance if I forget something. I've gotten a fair number of emails from students about, like what about this grade thing and stuff. And it's just kind of it's a lot to keep track of, so I might need a reminder, and that's totally fine. So, well, my philosophy with stuff like that is it's always gonna end up in your favor, right? If I make a mistake or something. So I don't want you guys to be stressing that as we get towards the end of the quarter. Um, let's see. Do you guys have any questions or concerns about anything? Let's see. Yeah, it'd be easiest probably to set up a time we can talk on Teams. Krishna, if you have questions about stuff, um, maybe shoot me an email or a message in Teams would be ideal, and we can set up a time. So a number of students have set up times this week. They're tracking down like labs and stuff like that. So that seems to work fairly well. Um, okay, so let's talk about rotational motion. And I think I had been arguing to you on Monday that this is that there's a lot of similarities, a lot of overlap with stuff that you already know. And for that reason, I think this subject is really a nice one to kind of close the quarter with. So we're going to look first at a couple more problems. Recall the last thing basically that we had introduced was these kinematics expressions. And so the first thing I wanted to do today was just to give us a few questions to look at to kind of exercise these ideas. But the thing that sort of jumps out at us when looking at this is that they have the exact same mathematical form as our kinematics expressions from chapter 2, except we're talking about angular quantities. So recall, this is basically the same thing you get when instead of x, you have theta. Instead of velocity, you have omega. And instead of acceleration, you have alpha, angular acceleration. So let's look at a couple more problems in this vein. Let's here. I think this is the one. Okay. So here is a question for you. Do you guys know what a centrifuge is? Have you heard of a centrifuge before? Um, so you may have run into this before. Like if you give blood, you know, they'll do this thing where they'll put the, or if you get your blood tested or something, they'll put a little tube of blood in this thing and it'll spin it around real fast, and it will separate the components based on their density. And this is one application of a centrifuge. There's other ones too, but it's basically a spinning thing that's used to separate different components of a mixture. And so this question has us practice our rotational kinematics in the context of a centrifuge. So there's different configurations. My attempts to draw this are probably going to look like not very good, but it's sort of like it might be on a bench top or something, and there would be like spots for the tubes, and you can imagine the tubes kind of sits in here like this, and then this whole thing would spin around, and it would separate the contents of the tubes, sort of like that. So for the purposes of this question, we're talking about, instead of A, we're talking about alpha, angular acceleration, and we're given a RPM, so this would be an angular speed or frequency and an amount of time. And so they're asking us for how many revolutions does this entail? And really what that is a way of asking us for what total angle does the centrifuge turn through if we accelerate uniformly from rest to 15,000 RPM. 15,000 is a big number, but centrifuges can spin really, really fast in this time. So basically what they're asking us for is, what is theta? So we can use our expression for theta here. Why am I writing so big? Basically, the theta is the initial angular velocity times t plus 1/2 alpha t squared. We know t. If it's starting from rest, that means that this would be 0. But we don't actually know alpha. But we have but we can calculate it here really quickly. So alpha, if it's uniform, we know that we can just calculate the average, and that's given by the change in omega over change in time. So it's directly analogous to average acceleration being given by change in velocity over change in time. So probably the trick though is that our units are sort of strange. So this is in RPMs. So we can't just divide 15,000 RPM. So let me put this as revolutions per minute divided by 220 seconds, because notice these units are not, they don't agree. So we're going to have to multiply this by a factor. We need to multiply this by 2 pi. That'll change revolutions. So you can think of this as 2 pi angle per revolution. And we're going to divide by 60 because there are 60 seconds per minute. So when we multiply by that, that'll give us a result that's in revolutions per second squared, which is or not revolutions, sorry, radians per second squared, which is the unit that we want for alpha. So if we multiply this stuff out, we find that alpha is 7.1 rads per second squared. So now we have alpha. We can stick it in here and solve then for theta. So our alpha our time so this, when we multiply this out, this would give us a result that's in theta. So this gives us 1.7 times 10 to the 5 radians. It's an angle. But really the question is asking us for how many revolutions. So recall that you're going to have 2 pi per revolution. So what we do then is if we divide this number by 2 pi, that'll give us 27,500 revolutions. Okay. So a couple things that we've exercised in this question. We've used this expression for theta as a function of omega and alpha and time. We've talked about angular acceleration, and we've distinguished between revolutions and radians. Yeah, so what do you think of this question? Or what questions do you have about this? Yeah, so if it didn't accelerate uniformly, we would need to know the function. We'd have to integrate rather than, we couldn't make use of this expression for theta. Recall, way back how we've said, we've used this expression that v is at, but this is under the assumption that this is really all these algebraic expressions are under the assumption that the acceleration is constant. If you had alpha that was a function, or acceleration for that matter, to get velocity more generally, you'd have to integrate. And you could think of this as being, this would be a function. And then you would integrate again to get x. It's the same story with this. You'd have to integrate alpha to get omega and integrate omega to get theta. Let's see. So revolutions per minute times 2 pi. Well, revolutions per minute times 2 pi over 60 seconds. Here, let me write this in a little more detail. So we had 15,000 revolutions per minute times 2 pi radians per revolution times 1 minute contains 60 seconds. So this way you can see how all the units cancel and you're left with something that's radians per second. I can be more explicit about that here. Yeah, that's a very, very common conversion that you end up making with these rotational problems, just because RPMs are so ubiquitous compared to radians per second. It's just like, if you were given all your problems in miles per hour, because it's a familiar unit, but really you know that you want to work in meters per second or something like that. Questions? Those are some good questions. So let me show you another one. Let's see if we can find it here. Where did it go? This is sort of a similar question, still talking about rotational kinematics. So in this question, we have a cooling fan is turned off when it's running at 800. When it's running at 850 revolutions per minute. It turns 1,350 revolutions before it comes to a stop. What is the fan's angular acceleration? Again, we're assuming it's constant so that we can solve the problem algebraically. And how long will it take for the fan to come to a stop? Okay, so, man, my ability to draw this is not going to probably be very good, but we have a fan that's whipping around. And wait a second. Yeah, that's right. The fan's whipping around, and then it comes to a stop. The thing is rotating at 850 RPM. And what we're looking for is the angular acceleration as it slows down. And this 850 RPM, really, that's the initial angular frequency, angular speed. So this isn't an example of a problem that we can use our... remember, there were often problems where, when we were talking about kinematics, where you didn't have the time, but you had the distance and the velocity, say, and you wanted to solve for one. You could solve problems without where you didn't know time. Well, we can use the angular analog of that in this problem. Oops. So recall the final angular speed is going to equal the initial squared plus 2 alpha theta. So the final is going to be 0 because it's coming to a stop. So then we can solve this for alpha. We know theta because we know how many revolutions it makes. We know the initial speed. We're going to have to convert some units again, but that's not a big deal. So if we solve this for alpha, it's going to be negative omega naught squared over 2 theta. This is negative, so omega naught, again, 850 revolutions per minute. We're going to multiply by our factor of 2 pi over 60 to convert this into radians per second. And that quantity squared. And then we're going to divide by 2 times 1350 revolutions. So that's 1350 revolutions times 2 pi radians per revolution to make sure that we're in units of angle. When we multiply this stuff out, you find that alpha is negative 0.475 rads per second squared. Okay. So this is our alpha. Assuming that it's constant. And then how long is it going to take to come to a stop? Well, this is, we can make use of our omega is going to be an initial, omega initial plus alpha t. So now that we know alpha, that was 0. So we can solve this for t. Let's see here. 850 times 2 pi over 60. Negative. Notice it'll be a negative divided by negative, so we'll get a positive number, which is what we expect. Notice here also that the units will cancel such that we have just seconds, which is what we want. When we crunch the numbers here, we find that this is 191 seconds. So a little over 3 minutes. So this is another example of rotational kinematics. Questions? Or what questions do you have? So this, again, it exercises this unit conversion like you were asking about, Krishna. We get to make use of, in this problem, we get to make use of this, our time-free expression. So you can see, as you work problems and stuff, you would make use of your different algebraic kinematic expressions. And there's a few problems in the homework assignment this week, I think, that are this kind of thing. What do you think? Fairly sort of familiar because it's like your kinematics? Feel like you would be able to solve questions on this? Yeah, okay. So it's sort of different, sort of familiar. Well, let's talk about. So recall when we talked about kinematics originally, all of this so far has been describing motion. Yeah. You're not going to be expected to do real detailed calculations with this stuff. You need to just kind of know the basics. You would have to be able to make sure that you're in the right units, I guess, but as we get towards the end, I mean, I can't really justify asking you really complex questions about stuff that you've only, dabbled with, only seen a little bit of. So, yeah, don't worry too much about doing really detailed calculations. But there are a few questions in the homework, so that should give you a sense of kind of what you need to know. So, kinematics is describing motion. Man, I cannot get. But I think the natural question that comes at with this is, but what causes it? And when we were talking about acceleration, velocity, displacement, the thing that caused acceleration was force. So remember, uh, acceleration was caused by force. And this was, way back in like chapter 4. And we talked about Newton's second law, that F equals ma. Well, in this situation, an angular acceleration is caused by a torque. And what is a torque? Well, torque, we use a big tau, or a capital T if you want, is a length times the component of force that's perpendicular to that length. And you can think of this in a couple of ways. You can think of this as R. I'll draw a picture in a second here to give you kind of an idea, a better idea. You can think of this as RF sine theta. And actually, there's a more mathematically rigorous and powerful way, as there often is, to describe this, which is with the cross product, that it's R cross F. Actually, so I don't think we're going to have much time to talk about the cross product, but this is an example calculating torque of an application of the cross product. So let me just give you kind of a cartoon of what this looks like. So a good sort of intuitive example, I think, to think about is you imagine like a wrench. Oh, wow, if I can draw a wrench here. Oh my gosh. All right, 1 second. So the wrench is going to have some length. We'll call that R. So sometimes they talk about this as being like the lever arm, which is sort of an intuitive description. And then you apply a force to this wrench. It's not the length of the wrench per se, it's the length where you apply the force. So example, this could be R2 if that's where you were applying the force, but you get the idea. So if the force is perpendicular to the wrench, then you can see this would just be R F sine of 90 degrees would give you 1. So this would just become R times F. But you can imagine, like, if you pushed on this at an angle, suppose that you pushed on it like this. Now, although R is the same, we're pushing on at the same length. F is now at an angle, so even if the forces were the same size, this is going to be less. And you can imagine different examples, like if you were to push on this like this, in this situation, the theta would be 180 degrees. And so in this case, sine of 180 degrees would be 0. So this whole thing would be 0. In other words, if you're pushing, if there's no component of the force that's perpendicular to R, if R and F are parallel, then there's going to be no torque. So that's sort of the definition of torque. And to complete our analogy, we described how a force causes a mass times force equals mass times acceleration. A force causes an acceleration. Well, a torque causes an angular acceleration, but instead of mass, we have something called I, and this is the moment of inertia. So a moment of inertia, well, it's the rotational equivalent of mass. And it contains information about the geometry, is the qualitative key. So, a long story short, it depends on how your mass is organized, how an object is arranged. Its moment of inertia will be different. So, you could have the same amount of mass, but depending on how it's configured, you get a different moment of inertia. For the same torque, you would have a different angular acceleration. So, for example, if you have, so let me just show you an example, and then we'll talk about where this comes from. It's kind of a cool application of calculus, actually. So if you have a solid, so let me do my best to draw this here. Consider a solid cylinder. That you would rotate around its center. So imagine like a can of soup or something that's rotating around the axis of the cylinder. Maybe not something that contains liquid. That might be kind of confusing. Think of like, I don't know, a wheel of cheese or something that's solid. This is going to have a moment of inertia of 1/2 the mass of that object times its radius, where the radius is that radius. This would be different even for the same. Let me try and draw this. So imagine everything is the same here, except instead of this being, oh man, this is pretty rough. Trying my ability to sketch something. So instead of this being solid, suppose that it's like a hoop, like an empty can, right? For the same mass, though. In this case, the moment of inertia, sorry, it's not 1/2. It's mr squared. So this is, you're rotating it around the same. Everything is the same, except, it's the same radius, it's the same mass, except the mass is all packed on the edge. In this case, the moment of inertia is mr squared. Now, what this tells you is that for the same torque, in other words, for the same torque, the solid one is going to experience a larger angular acceleration than the hoop, because the solid one has a smaller moment of inertia. So in other words, for the same t, because recall the torque is I alpha. So if I was to get bigger, alpha would get smaller and vice versa. So kind of the natural question then is, where does this I come from? How do we calculate it? So yeah, you would be given the moment of inertia. I'm not going to ask you to calculate it, although I'll show you here quick where it comes from, because I think it's kind of neat to see this connection to calculus. That said, have you ever had to integrate? Have you ever had to find these in your calc classes? Find a moment of inertia? Have you ever had to? So it's kind of a cool question. I will show you an example, just because I think it's neat to see an example where something like an integral, which oftentimes we think of as being kind of, or it may seem sort of abstract because it's like, well, okay, why do I actually care about this though? And this would be an example of how you use integration to find a quantity of interest. So let me show you. So where does the moment of inertia come from? You can think of it as if you had just a mass. If I can draw here, give me a second. Oh my God. So suppose you just had a mass. If we wanted to accelerate this thing, so think about think it's a point mass, and you're trying to accelerate it. And when I'm talking about acceleration, I mean the tangential acceleration. You're trying to speed it up. We're not talking about the centripetal acceleration in this case. So if you were doing that with a force, you know that the force would equal the mass times that tangential acceleration. Now, we know that we can write tangential acceleration as r alpha. So in other words, we could write this as m r alpha. Now, we've also just introduced this idea of torque. So supposing that the force and, here's our radius are perpendicular, the force times the radius would equal the torque. And that would equal mr squared alpha. So this mr squared for a point, this is the moment of inertia. Now, this is the case where we just have a single point, right? So this isn't exactly what we usually talk about. So instead, imagine that we had something where we had multiple masses. Suppose we had multiple masses. Now, in this case, the moment of inertia, where we want to accelerate, they're connected or something. You want to accelerate them, spin them up. The moment of inertia in this case would be the sum of the moments of inertia for each. And you can kind of see, I suspect, where this is going. If you were talking about, instead of a collection of points, you started talking about a solid object, this moment of inertia becomes an integral. So you would imagine having to, like integrate over the whole object. You have to know how far each differential chunk of mass is from the center, from its axis of rotation, and then you would have to integrate over the whole object. Well, let me show you what that looks like for our cylinder. So with the cylinder, like I told you what the moment of inertia for this thing is, but you can think of this as, a cylinder of length L. It's got some radius R, capital R. Basically our task here is we need to apply this integral. We need to integrate over the whole mass of the cylinder, R squared dm. So, in other words, we need to make dm and dr, we have to make those compatible so that we can integrate. And the thing that we normally do in this is we can express dm in terms of the geometry. So dm is going to equal a rho, so where rho is the density, times a dv, so times a differential volume. And here, let me draw you a picture. So if we're talking about, so notice this thing has cylindrical symmetry, first of all. If we're talking about a differential volume, you can think of that as like a little shell of volume. And the volume of that, so think of this as, let me try and draw this carefully. The width of this would be dr. So what this becomes is rho times, so the circumference of that, which would be 2 pi r, times the thickness, dr. And then technically this thing has length too, so there would be a factor of L. So in other words, this is just to argue that we can write dm in terms of dr. So then this becomes, now, and notice also that if we want to integrate over the whole mass, instead of from 0 to m, our integral becomes from 0 to capital R. And then this becomes r squared rho 2 pi r dr. We can move let's move our L up here because it's a constant. And then notice most of this stuff is constant. So let's pull out our factor of 2 pi L rho. And then we have just an integral of from 0 to capital R of r squared times r, so r cubed dr. You know the integral of that. What's the integral of r cubed? You guys know this. What's the integral of r cubed? Yeah, exactly. So the integral of r cubed will give you a factor of r to the 4th over 4. You're integrating from 0 to r, so in other words, this will become capital R. Here, I'll write it in 2 steps here. So when you evaluate this, you'd pick up 0 from the lower limit because you're starting at the center, and then this would become 2 pi L rho r to the 4th over 4. And we can simplify this by noting what is density in terms of the quantities that we know. The density is mass per volume, right? Well, what's the mass? The total mass will just be m, capital M. The volume, what's the volume of a cylinder? 2 pi, no, not 2 pi, pi r squared, the area, times the length. So this is mass per volume. If we put this in, substitute this in for rho, 2 pi L times capital M pi r squared L. Notice, oh, sorry, I should say this is capital R. You know, if you have your cylinder has a radius of capital R and a length of L, this will be pi r squared L. So when we put that in for rho in our expression after our integration, notice like most everything here is going to cancel out. We lose our factor of L. We lose our factor of pi. 2 over 4 will become 1/2. We'll still have the capital M. And then r to the 4th over r squared will give you a factor of r squared. And this is the moment of inertia for a cylinder when you're rotating it about its axis like that. So this is an example of calculating a moment of inertia. Like I said, I wouldn't expect you to do this, but I think it's nice to see a connection to calculus, and it's just yet another example of how calculus is really kind of the natural language for physics. So I wouldn't be surprised if you encounter a problem that asks you to calculate a moment of inertia in your math classes, for example. But next time we will look at a couple torque problems and talk about a couple other things, and then that'll be it. So I'm trying to be better about ending on time. So next time, we'll look at torque problems. So you can read, something like sections. Well, read chapter 10. Looking at those torque problems, that'll give you everything that you need to finish the homework assignment for this stuff. But I suspect if you look at that, you'll see it's a shorter one this week. Yeah. So what questions do you have? Did that moment of inertia calculation seem logical to you, or did it seem like a jump? What do you think? Yeah, I'm not going to ask you to do any integration. I'm not going to ask you to calculate moments of inertia. I just wanted you to see that once where it's coming from. You can imagine generalizing this for different geometries, right? If you had, different shapes, you can figure out how to express that shape as an integral and integrate over it, and that would allow you to calculate moments of inertia for different things. But actually, I should mention there's a chart in your textbook. If you read the chapter, you'll see this, but there's a list of moments of inertia that's given there. Yeah. Usually you'll be given an expression like this, an algebraic expression like, for a cylinder that has such and such mass and such radius, and then you would have to calculate. I'll show you next time a problem that's just like that. But yeah, in theory, you could be given a number too. A moment of inertia of some kilogram meters squared. But generally, they're not stated like that because I think it's a little bit weird. Or to put it another way, it's nice to have the algebraic expression because it gives you some insight about the shape and stuff. Yeah, so we'll look at a couple problems tomorrow. I can tell you right now, it's chapters 1 through 10. I mean, I don't know the exact weight of every chapter. That's kind of a tough question because a lot of the chapters use ideas from other chapters, right? It's not like you could do chapter 4 without knowing something from chapter 2 and 3, so it's a little bit difficult to say exactly. But you're basically responsible for the first 10 chapters of the book. I mean, you're not responsible for sections that we didn't cover. And don't worry. We'll spend a whole class period, at least a whole class period next week on Monday, uh, looking at examples, and we could spend more than one depending on demand. So I don't mean to just brush off your question, Carolina, but we'll be looking at review. We'll give you some stuff to hopefully you'll have a better sense of what to expect on the final. Because well, the last class where we're talking about new stuff is tomorrow, but on Monday we'll do a review. And then your final will be that week. will be next week, of course, but so the reason that we're doing that is because I think it's a good compromise because we're missing a week of class, right? So we're not going to talk about anything new the last week. I think that would be a bad idea because just everybody is going to have finals and their last week of class at the same time. But since we're missing a week, we're not going to do review before the last week. Um, does that clarify that? Okay, so we can chat more too via Teams, etc. if you have questions. I am going to end the stream now. So have an excellent day, and we will chat tomorrow.